here on a panel to provide us with their perspective on the meeting from their various vantage points on the whole question of lunar formation with Dave, Mattia, reflections on the problems with the dynamics and tidal evolution, and George on the synergy that we saw in the meeting between science and history of science and how to move forward with that as a university and generally perhaps as an interesting initiative for other such meetings. So please, guys.
So as I see it, the story of the origin of the moon has happened in 3 stages. In the first stage, there were not a lot of people thinking about it, but to the extent that people thought about it, there were a variety of alternatives out there about the origin of the moon. But then, beginning in 1974, there was a presentation by Bill Hartman and simultaneously work from Al Cameron and Bill Ward, which pointed to the dynamic attractiveness of a giant impact. The idea that, is this on or do I have to turn it on? The idea that it's a perfectly reasonable thing to happen when the terrestrial planets form to have an impact of the kind that would provide the observed angular momentum of the Earth-Moon system. And this led in 1984 to a conference in Kona, Hawaii, where a bunch of people turned up, more or less reaching the same conclusion. And I was at that meeting, so I remember well what happened. There were others who turned up with the alternatives, capture, and binary accretion, and so forth, the things that Simon talked about. But there was a broad consensus that the giant impact was a natural thing, that it was an attractive, dynamical explanation. It's interesting that at that meeting, there were some prominent geochemists who did not buy the argument. So this groundswell of interest actually was driven by dynamics. Geochemists at that point did not have a strong basis for expressing concern, but they were nonetheless concerned. Ted Ringwood liked the idea of building the moon from multiple impacts. I still think that has problems, but the fact remains that the geochemists were looking for alternatives. The same was true with Mike Drake and other people who actually attended that meeting. There is an irony in this story, and the irony, of course, is that we are now talking about an impact origin that throws away the very thing that drove the story in the first place. The coincidence of the angular momentum of the Earth-Moon system and what you would get with a Mars-sized embryo hitting the Earth obliquely. The one-line calculation of Bill Ward and Al Cameron is now being put in question. Anyway, that was the first stage of transitioning to the giant impact. And the second stage was the widespread acceptance and grudging acceptance maybe from geochemists for a while of what we call the canonical giant impact, the one I just mentioned, the one that motivated the one-line calculation by Bill Ward and Al Cameron. Leading, of course, to Robin Canop's work, actually begun by Al Cameron, because Al was doing it on his IBM PCs that were hitting his office at Harvard at the Center for Astrophysics, amazing place. And then, of course, we had this gradual recognition beginning 15, 20 years ago that there was a problem. And the problem was expressed at that point primarily with isotopes, not tungsten so much, but with oxygen and then with other stable isotopes. And this came from the geochemists, and it happened. Why? Because the geochemists developed better analytical techniques, they could go to the very same samples. There were no new samples. It was the Apollo rocks, the same ones that had been studied in the 70s. They went back with better techniques and they got more accurate answers. They went after alternative measurements, which confirmed this similarity of the Earth and the Moon, which was striking in the context of what we knew about most meteorites and what we knew especially about the emerging large difference between the Earth and Mars. And so that led to this third stage where we went from, so the first stage was everything's possible. Second stage was a canonical giant impact. Third stage was let's look for something different, and that was Cook and Stewart, and also represented by Simon Locke's work. I think the conclusion of that effort is not yet with us, but the change was driven by the geochemical data. There were other ideas out there about mixing. I got involved in that. I think it is correct that there are difficulties, that there are some attractive features with the new picture, coming mainly with Cook and Stewart and then with the detailed dynamical story that Simon Locke has put together for the giant impact. I don't think we know what the correct answer is yet. I rather like what the geochemists first said when I poked at them 15 or 20 years ago, even though it's not a complete answer. And the response I got from people like John Euler at that point was, well, let's just make the projectile similar to the Earth. And Simon has explained why that's not an entirely satisfying answer. It does raise issues about what to do with tungsten. Why is tungsten so similar between the Earth and the Moon? But in terms of the other things, and looking at meteorites, I think Niccolo Dauphin has actually put together a rather nice story with the one outlier, and he admits it, and Simon mentioned it, which is the tungsten. Maybe coincidences are okay. So I don't think the canonical story has been destroyed. I think the new story is unproven. The new story has several aspects that you can question. The new story of a high energy impact, very rapid rotation, has, to my mind, several probabilistic aspects that are questionable, that they might be fairly low probability events, that you get the right kind of impact, which looks to me to be a little bit improbable, to get the angular momentum extracted to the right extent, a little bit improbable. There are some questions about what actually happens in the disk. How does the moon actually form? By the way, that's true in all of the stories. There's a problem about understanding the disk. And then, of course, there is this unease, at least that I have, that we don't fully understand the moon and we don't fully understand the Earth. In other words, are we dealing with a full deck of cards? Do we actually know the data? As I see it right now, in summary, yes, there was a giant impact, and that was the origin of the moon. But a big question mark about the specific giant impact that did the deed. And I raised the issue of more data. I think we need to go back to the moon. I think we need to understand the Earth better. It's not clear to me that these things will be resolved in my lifetime.
Thank you. So I'm going to disagree with Dave on one thing, that I think the canonical impact has been broken dynamically. So interesting thing about dynamics. So as Dave says, early on it was everything goes. For dynamics, it sounds like it's not like that, because we have this foundational text of Goldrake for our field, which was confirmed by work by Jihad and Jack in the 90s, and it just seemed to be a kind of theory with lots of approximations. With every approximation was just right, and everything turned out correct. Now, if you actually dig deeper into ADS, there was lots of stuff in those days that was quite wild and quite wrong. So we just remember the ones that were right. So there was a little bit of everything goes in dynamics, but then by the time, by this century, it was very, very well established that the Goldrake evolution is correct under assumptions that it had. So, since I do dynamics, I don't like something being solved because I want to do something. And if it's solved, then there's nothing for me to do. So to me, it looks like that all these new processes we're talking about, and the key to them to some extent is the inclination damping, but also there is a cross connection with the composition, angular momentum, and other things, have actually given that there is something here that we can't go back and we don't know what the answer is. So comparing Jack's results and mine for some of the initial conditions, like we had the same ingredients, only our models were slightly different, and we already got some of the different results, and we still have to throw in planetesimal flybys, which they happened. The only question is how important they were and when exactly they happened. Then, the moon interacted with the disk. Most of the tidal evolution stuff assumes that the moon forms, disk is gone, and then we do our integration. And then, I talked about lunar core. You can always add more bells and whistles, but to me, it just means that the field is wide open. I don't think it's anything goes anymore. It's we have established quite a few things, and every model that tries to be competitive now has to have lots of elements. But to me, it looks like a good, healthy field with a perspective of being productive in the next decades.
George?
Okay. I only speak as my experience here and what I learned over the last 2-3 days. And as a historian, I can tell you that I have learned a whole lot. But about 4 or 5 major points that I think are significant and I can share with you, and I think are very useful. First, I have learned that when Ptolemy in the 2nd century AD literally said that in order to get precise results, we need to get historical observations as well, and the farther the distance between them, the more precise are the results. And he actually did use ancient Babylonian observations that went back to 747 BC, and he was doing his observations in about 150 AD. So there's almost 1,000 years. That is, but now what I learned is that a period of 1,000 years is really nothing. You have to wait a couple of eons or a couple of billion years, and then, to my surprise, turns out that the moon is still evolving. Not only it, the Earth is still evolving. We are still in transition, so there is nothing that we can feel safe and we feel that this is it. Unlike the religious minds and the ideological historians who always feel that they are sure, they got the data, it's all fixed, they know that the last what it is. One surprise that I learned, which I think was very, very useful for me, and I hope in the future I will come to conferences of this nature to learn another surprise. I thought that when Ptolemy tried to explain why at 90 degrees the moon actually exhibits a variation between its real motion and its mean motion, a variation of 7 degrees and 40 minutes, I thought that was probably fictitious. Ptolemy probably didn't know how to do the computer, but then I was assured that at 90 degrees, in fact, there is a variation in the positioning of the moon, and as a result, it's a real thing. So the perigee of the moon that is visible at 90 degrees and hence detectable is not fiction. So what Ptolemy was, it's only the problem, it looks to me like when Ptolemy was trying to solve it, he was just trying to solve it with the wrong methods. And one could do better, and I think I could show you that it was better. The last thing that I also still hope in the future conference, I would also learn about it. There is this nasty planet that is called Mercury. And I'm sure that all of us who have ever looked at the historical descriptions of the movements of Mercury would agree with Copernicus to say that this is the planet that gave him the greatest headache. And to a great extent, I was told only because in reality it's so close to the sun, it's hard to observe, so the data that Ptolemy got for the movement of Mercury ended up with two perigees at 120 degrees away from the apogee on each side and almost symmetrical. Of course, you love symmetry in this case. So I had 120 degrees, and I am hoping that one day I will find in a conference like this that there will be an explanation as to why this 120 degrees seems to be significant rather than the 180 or the 90 as in the case of the moon. Ptolemy decided actually to use the same mechanism that he used for the moon, to drag the whole epicycle mechanism closer to the Earth, but at 120 degrees rather than 180 degrees where it would have made sense to the perigee. So there is still this puzzle, and I hope at some point I would learn a little bit more about the real movement, meaning real again as much as we can get, and hope movements that are within a human scale of history in terms of, or human scale doesn't mean anything, it's just like a blink. Within a couple of eons, how they move. But it is still a puzzle, and it is a puzzle that continued to plague astronomers throughout history who tried to understand how this planet actually moves and why it exhibits these strange variations at such odd numbers like 120 degrees and so on. That, I think, is, to me, the most outstanding things that I feel that I need to attend more conferences like that. Historians should not sit in a room and close themselves only with manuscripts that they read from the past, because what these conferences do, they shed light on these manuscripts as well. So now we can understand a little bit of why they were struggling, why they were trying to solve these problems, and sometimes successful, sometimes unsuccessful. I also learned something else by way of a methodology, which I think is very useful. Every single person who came and made a presentation here, they kept saying, we think so, or we don't know, or meaning the attitude of knowledge growing in the process, they don't shy away from saying we don't know. While when I go to similar conferences, especially between historians who are ideologically driven to say that nobody could accuse of Copernicus ever taking a theorem from somebody else. He created everything from scratch, meaning those kind of people who simplify history so much, they should learn some humility by coming to conferences like that, that there is a whole lot of material that we don't know, even in the historical sources, even in the manuscripts that we have them in his own handwriting, we still don't understand it very well, and we should attempt to at least pause with this kind of humility, rather than be ideologically assertive at this level. To me, these are much more important. Of course, the actual nitty-gritty of the physics went all over my head because I'm not a trained physicist. I only had, freshman and sophomore physics, did just about it. As a math major, again, you thought of it as applied mathematics. To hell with it, it's not important. So you just take the mathematics part. Then, only recently I began to figure out that the best physics is really in mathematics. It's not physics per se. All of these things, also the shuffling and the relationships of the sciences to each other, all of this is news to me. So I learned a whole lot. I want to thank Jihad for organizing this. And again, I have to be honest, like when about 2 years ago, we started discussing this, and he proposed these ideas that it may make sense to think of it in cultural terms, historical terms, astrophysical terms, dynamic terms, all of that. At the time, I said, well, there he goes again. Jihad is trying to be extremely out of his normal dig, and he is doing something completely new. But I never thought that he would pull it out. And actually, he pulled it out, and it is damn good. In fact, if I knew then what I know now, I would have encouraged him even more to simply go ahead, expand it into 2 weeks, make a seminar out of it for a whole semester, get a grant from, instead of wasting money on all sorts of other things to see if the female-to-male ratio changes the education in the classroom. That I think is totally wasted money, and get money to actually ask serious questions and things like that. But we learn. I mean, with time, we actually learn. So I wish you well. I thank you again, Jihad. I thank you all for actually teaching me a whole lot, despite the fact I admit that most of the material went right over my head, but every now and then I caught something. And these few nuggets that I picked up, I'm still waiting for the double perigee of Mercury. Someday somebody is going to explain it to me. Why is there a double perigee? The only planet that exhibits, by Ptolemy's data, the only planet that exhibits double perigees. I have an assignment for you, and I hope by next week I have an answer.
That was
Thank
great.
you so much.
Thank you, everyone. Yes, please.
I don't know about the double perigee of Mercury, but I'm really astonished that this crowd was accused of humility. It doesn't happen. Thank you.
You start every statement by saying, I don't know, but how much more human you want to be.
If we need to have the return conference, we go and understand not humility. And we learn about ourselves.
So any further comments from the audience? Alessandro, yes, sure.
So Dave proposed to resurrect the fast solution to the isotope problem, isotope identity of the Earth and the Moon. I think the fast model is purely cosmochemical and ignores dynamics completely. So it's extremely hard in simulation of terrestrial planet formation to grow planets out of a unique reservoir. We know there are plenty of reservoirs in the inner solar system represented by different kinds of meteorites, and keeping them isolated as planets are growing and scattering material around is awfully hard. And in addition, ancestral chondrites are a good analog for the Earth in terms of isotopes, but a very bad analog of the Earth in terms of chemistry. And even some differences in isotopes emerge. So it's not even ancestral chondrites that can be the solution. It's something else we don't know. So the famous Earth chondrites or Mike Drake. And then you need to grow planets out entirely of this material without leaving behind any bits in the asteroid belt. And so I think this is a very implausible solution. I would like to point out something that Kruger et al. Pointed out in their manuscript on tungsten, that the impactor, which brings about 5–10% of the mass of the Earth, is a big contaminant of the Earth. So you don't just need to eject terrestrial material in the disk to form the Moon, because then the Moon would be equal to the pre-impact Earth, but the Earth changes with the addition of the material of the impactor. So you need first to mix impactor and proto-Earth, and then out of that mixture produce the lunar material. So this really points out that in some fashion there must be a great degree of equilibration, as you pointed out with Kaveh. We just need to solve the bottleneck to understand the equilibration. So there was the bottleneck of angular momentum difference between the disk and the Earth that was pointed out by Melosh, that I think the Synestia solves very elegantly. There are still some problems with the stratification of the Earth that we learned today, actually. So, but maybe, we can have more shear in the Earth. You assume that the Earth is rigidly rotating, but how realistic is that? Maybe because the impact is partially oblique, you get some shear internal to the Earth, which stimulates turbulence, and you can have more mixing within the Earth, and some technical issues to be solved. Basically, we don't know, but I think we are paving the way towards a solution. But I think the solution is equilibration. There is no other rational solutions to the data and they are compatible with chemistry, elementary chemistry, isotopic chemistry, and dynamics at the same time.
So I'm going to make the politician's answer, which is I think that all of these things are important. So Dave and Miki Nakajima pointed out that there is enough kinetic energy and enough shear to mix the entire body in these high momentum impacts, and even in the canonical impact. The issue is that shear is distributed very heterogeneously around the planet. And so to answer the question, probably we do need to go and look at numerical codes, and the numerical codes do a terrible job of mixing. So I think that there is a lot of, I have sort of a lot of optimism that the amount of mixing that happens during the impact we are currently underestimating by some degree. Quantifying that will be a very large challenge, and I will foresee many false prophets before that people will try and do things with codes that are not they are not able to resolve, and it will take a lot of careful work to do it. However, I do agree with Dave that I think Nicolas' suggestion is an important part of the problem. That we are now at a level where the isotopic measurements are so precise that the two colliding bodies have to be somewhat similar. They don't have to be ansatite chondrite necessarily, but they definitely, they definitely can't be Mars. And so I think that the answer lies probably in between those two. But taking Nicolas' arguments the other way, there's something incredibly interesting about ansatite chondrites, because chemically they are different, and they've obviously experienced lots of different chemical processes, sulfidation and various other things. But they are something that looks very similar to Earth that is hanging around. And so there was obviously material that looked very much like Earth around. And so maybe you can actually flip that and say, what is the relevant origin of the ansatite chondrites relative to Earth? I think that would be sort of as interesting to look at that angle than sort of just invoking them as a way of solving the moon problem, actually using them as a way of investigating the dynamics. I mean, you have to have a surviving population that looks similar to Earth.
So, I think in a sense I'm going to agree with Morby in his specific criticism of Nicolas Dauphin. However, I'm also going to say, and I think in agreement with Simon, that the geochemists are making a valid point. Here's the way I see it. Geochemists are fond of trying to understand what they see about them using the things that they can get their hands on. And that could well be a mistake. And in that sense, I'm agreeing with Morby that there has been a long-standing tradition, which I don't like, in which people look at meteorites and then try to understand the terrestrial planets. And the reality is that we don't have a good basis at the moment for understanding exactly how ansatite chondrites came about and so on and so forth. And we don't know at this point whether it is appropriate to look to the meteorites as a basis for understanding the composition of the Earth and the Moon. So in that sense, I'm agreeing with the specifics of the criticism. However, I still think that it's an open question as to whether the Earth and the Moon were isotopically similar upon impact to make the Moon. And so in that sense, I still think he had a valid point to make. On the mixing question, my take on it, which actually is different, people often quote Jay Malash on this. I actually never liked that paper, and I think he missed the point largely. The key issue still is the extent to which the deep interior of the Earth can communicate with the disk. And he may have mentioned that in passing, but that was not the main quote in this paper. And that is a key issue. That is hard to do. Following the giant impact, the matter was actually stable because it has higher entropy in the outer regions. I'm talking about the canonical model. And it's actually difficult to equilibrate oxygen isotopes between the deep part of the Earth's mantle and the disk during the time that the Moon formed. So I think that is a legitimate criticism. The Synyeska model, the model that Simon talked about, may not solve all problems, but it has one attractive aspect, which is the more direct connection between the disk and the planet, because there's no boundary layer that you have to place in between them. There are fluid dynamical aspects we don't understand, but it would seem very likely that if you have a giant impact in which the Earth is already rapidly rotating, that helps enormously on the mixing problem.
So in context of like what else we can use to improve our models and maybe get mixing during the impact is just going 3D. Like almost everything we explored so far has been in terms of vectors. Either non-rotating Earth hit by something, in which case you have only one axis of symmetry, or in case, like in Chuck and Stewart, we had a rotating, the main case was a rotating Earth that was already rapidly rotating, but it was hit with at the equator by a purely retrograde impactor. So this will be harder to simulate, but you know, certainly there was a pre-impact rotation, and then when the thing hit, there was more of a mess than we usually.
So I agree there's a huge parameter space to explore, and it's just difficult to get people to fund the computation time when you add an extra 3 variables. But there is a more fundamental aspect of understanding mixing, is that the codes cannot capture mixing as a process. They approximate it very well, but because SPH treats everything as tiny particles, there's no thermal exchange, there's no material exchange between those particles. So anything that is hotter will rise, and everything that's colder will sink with angular momentum constraints on that. And so things that could have been intimately mixed in the impact will be separated during the post-impact re-equilibration. So those, and also resolution dependent, because a lot of mixing is done through turbulence and cascades, and so if you're not resolving the lowest spatial dimensions, then you have issues getting to the macroscopic as well. This is a very known problem in computational fluid dynamics. And so there are other codes we can use, but they all come with their own set of assumptions about how material is mixed and their own limitations. So in Eulerian codes, you have to deal with what happens when 2 different materials pass into the same grid cell. Do you mix them? Do you partly mix them? And boundary tracking is incredibly hard in those codes. So there is obviously parameter space to explore. I think we just have to be very careful using the codes that we have and finding ways to place bounds, because I don't think we're ever gonna, saying I'm never gonna have the competence now, my code gives you the right answer. But you can definitely, I think, find ways to explore the range of possible outcomes by exploring the different treatments of mixing in each of these codes. And finding ways to parameterize some of the things that aren't captured. So I think it's not just a question of running the same codes more, it's a question of actually needing to model the physics better and more fundamentally, and probably accept the fact that we never will be able to do it. So we have to find ways of making a good approximation. I'm really bad. I'm really going to fail my memory. There was a point I was going to make and I forgot it.
May I add a few minutes to catch up? May I add one more remark to
Please, George. Yeah.
which it slipped my mind. Thing that I just learned this very morning from Professor Witt, is that the ecliptic inclination is variable. It's moving. This is good news, because when Ptolemy measured it, he ended up saying that it was 23 degrees and 51 minutes and 20 seconds. 700 years later. Now, my question is that within 700 to 800 years period, would it move significantly to make a difference in measurement, or is the method of measurement that Ptolemy had used, which were diagnosed to be faulty, is the cause of that? Because by then, about 830, Ptolemy was observing about 150. So you have 700 years separation. More or less, everybody found that ecliptic inclination to be only 23 degrees, 30 minutes, 35 minutes, 29 minutes, in that range, rather than 51 minutes, and so on. And of course, it raised a whole plethora of questions. How could Ptolemy the Wise make mistakes like this? Also, how could Ptolemy remain silent when the moon at quarter time did not look twice as big as it is? All of those questions historians worried about, and astronomers worried about to such an extent that they proposed a theory which is now defunct called a theory of trepidation, meaning that there is this oscillation, and then they concocted models for the movement of this ecliptic plane to actually account for those variations and so on. So this is an assignment, I think, on next one. I would like to know if this change in the inclination of the ecliptic, is it noticeable enough to be detected within a period of 700 to 800 years rather than 2 eons or 3?
I can say something there. I mean, I haven't worked on this, but my way more famous fellow countrymen did. So there are these things called Milankovitch cycles, which change the things like the obliquity of Earth slightly over, say, 100,000, 50,000 year timescales. But it's, I think right now it's below 1 degree. And so since it's about 100,000 years or something, I think that change of big fraction of a degree in under 1,000 years was a mistake. And if I remember correctly, trepidation was a term that went away at some point when they got new data.
Okay, so I'll say a few words. So I mean, the purpose of the meeting was to get a sense of where things stand, the state of the art in various fields, including history of science. And I speak for myself, George, that it was truly a pleasure having you with us, both as somebody who's somewhat far from the field, but also involved with people who helped make the field what it is over centuries. So, and your insights just now, I find them extremely valuable. When it comes to the science of the moon itself, I found myself seduced by things perhaps dynamical in nature, but certainly not explicitly dynamical. So I found Dave's discussion of the L=1 and its infestation very inspiring, and I will certainly be spending more time trying to understand more of the literature on this series of observations that he made, and certainly the kind of solutions he is proposing. I think there may be room for some progress in some directions, and I am very grateful for that beautiful talk of yours. And then on the magnetism side, I was also very interested to learn of the serious crisis in which the field is, the difficulty in trying to explain observations. Perhaps these observations will disappear once more careful measurements are made, I'm not sure. But certainly the whole business of a lunar dynamo or magnetization of lunar rocks is a beautiful problem for the decade, maybe two to come. So definitely an exciting direction. And then what Simon described took me back actually, and maybe Jack was thinking of the same thing when he asked of his ellipsoidal shape to Poincaré's and the whole business of figures of equilibrium, I suppose. And then I recalled that interesting simulation of Boss, I think in the 80s, in which an attempt to go at the fission theory actually produced a rather very similar evolution, allowing for slight viscosity in the idealized picture of ellipsoidal figures of equilibrium. So that was a very interesting simulation. I think it meant at the time a serious criticism of the fission approach to forming the moon. And the outcome of this, they didn't, I don't know how extensive the simulations were or how long they were carried, but it certainly showed that the pear-shaped instability that Poincaré had talked about, or the tearing mode that Poincaré had talked about, will not survive slight viscosity in the system and actually produce something akin to what you're describing, only I'm sure with much better simulation and resolution. So again, this seemed to me like a very interesting process harking back to earlier days, and I will be certainly looking much closer at the dynamics involved in at least the stage that nucleates your beautiful torus-shaped object. So this has been all very stimulating, and I have to continue dealing with dynamics because I have a young student who is keen on getting her hands into the problems, essentially Cassini states in secular dynamical settings. So I'll be discussing more with you guys before you disappear. And it's just been a truly wonderful pleasure having you with us for these last few days. A couple more days of discussion, I'm sure, and hopefully enjoying your visit to the country. So thank you all for coming and for contributing at a very high level to this wonderful discussion.
Well, thanks to you for organizing this. Very
Yes. That's more effective.
Thank
you, Hibam. Thank you, Hibam.
Yes, thank you so much. It's my pleasure to have you.
you.
So, Bas is ready.